You think you know how nuclear fusion works. Almost everyone does, and almost everyone's wrong not about the engineering details, but at the most fundamental level. The real answer to why is fusion so hard will shatter the model in your head. Richard Feynman saw this before anyone else. And what he discovered isn't just about fusion, it's about the very limits of what science can actually explain. One question brings down the entire popular model with a single sentence. If the sun's been doing nuclear fusion for billions of years, why do fusion reactors need to reach higher temperatures than the sun's core? Engineers on Earth need to reach 100 to 150 million degrees Celsius. The sun's core, around 15 million. So we need to be 10 times hotter than the star we're copying? That makes absolutely no sense, unless the popular explanation is fundamentally wrong. And it is. The model most people carry is simple. Heat hydrogen until it's plasma. Heat it enough, and atoms move too fast for electrical repulsion to stop them. They collide, fuse, release energy. It's the star in a jar narrative, clean, limitless energy, always just a decade away. That line's been a running joke in physics since the 1970s. But the problem isn't just technical difficulty. The mechanism people imagine isn't the actual mechanism. Fusion doesn't work because hot particles overcome the barrier. That's literally impossible at the sun's temperatures. When you understand this, the question changes. It's no longer, when will we achieve fusion? It becomes, wait, does the universe really work like this? Let's start at the beginning, with the real obstacle. Two protons try to get close. The electrostatic repulsion between them grows exponentially. That's the Coulomb barrier, the electrical wall protecting the nucleus. To fuse, they need to reach about 1 femtometer, 10 to 15 meters, where the strong nuclear force takes over. But first, they have to push through this wall of repulsion. Classical thermodynamics says, give particles enough energy to climb the barrier. More temperature, more kinetic energy, more collisions. That's the intuitive model. The problem? Calculate the actual height of the Coulomb barrier, then calculate the temperature needed for protons to overcome it classically. The number's terrifying. Trillions of degrees. Not 15 million. Trillions. So how does the sun achieve fusion at 15 million degrees? In 1928, George Gamow answered it with a discovery that changed everything. The protons don't climb the barrier. They go right through it. This is quantum tunneling, one of physics' strangest and most real phenomena. A quantum particle doesn't have a defined position. It has a wave function, a probability distribution. And that wave function doesn't stop at the barrier, it decays exponentially through it. There's a small but real probability that the proton appears on the other side without climbing over. The sun doesn't operate hot enough for protons to overcome the barrier classically. It operates at temperatures where quantum tunneling happens frequently enough. Solar fusion is quantum, not thermodynamic. Temperature matters because it determines kinetic energy, which affects tunneling probability described by the Gamow factor. This completely shatters the intuitive model. The star that warms our planet, that made all life on Earth possible, that converts 600 million tons of hydrogen into helium every second, works because the universe allows particles to pass through quantum barriers they should classically never be able to cross. The sun is a quantum machine operating on an astronomical scale. Now for the obvious question, if the sun uses quantum tunneling at relatively low temperatures, why can't we simply replicate that here? Why don't we operate reactors at 15 million degrees instead of 150 million? The answer is that we're trying to do something that seems simple, but is fundamentally different. The sun has 1.989 x 1030 kilograms of mass. To replicate its gravitational confinement, you'd need a mass comparable to a star. No material, no magnetic field, no engineering can match that on a human scale. We can't reproduce that amount of matter, but the sun also has 1057 protons. Tunneling probability for any individual pair, extremely low. A typical proton takes billions of years to find a partner and fuse. The sun works because it compensates extremely low probability plus absurd number of attempts per second. It's the law of large numbers applied to nuclear astrophysics. In an Earth-bound reactor, we don't have 1057 protons or stellar gravity. We have a human-sized chamber. We compensate for scale with temperature-pushing particles into the region where tunneling happens frequently enough to produce net energy. That's why we need 100 to 150 million degrees. Not to overcome the barrier classically, but to make tunneling probable enough inside a building-sized chamber. Now, the real engineering problem: at 150 million degrees, matter becomes plasma. The fourth state, electrons completely stripped from nuclei. No material on Earth survives direct contact with that. Tungsten melts at 3,422 degrees. We're talking about 150 million. How do you confine something that destroys any container the moment it touches it? Two fundamental approaches exist. First, magnetic confinement. Plasma is conductive, so intense magnetic fields force it to follow field lines instead of touching walls. The tokamak, a donut-shaped chamber with helical magnetic fields keeping plasma suspended. ITER, under construction in southern France with 35 nations and 20 billion euros invested, is the largest tokamak ever built. Second, inertial confinement. Compress and heat fuel so fast that fusion happens before plasma disperses. It's the hydrogen bomb principle, controlled. The NIF in Livermore uses 192 lasers to crush a tiny deuterium-tritium pellet. Here's where working in fusion gets precise. The Lawson criterion, developed in 1955, defines the threshold for net energy gain. It's not just temperature, it's the product of plasma density, confinement time, and temperature. Extreme temperature with brief confinement, you get nowhere. All three have to optimize simultaneously. Temperature is 1/3. Confinement and density are the other 2/3. This is the real challenge, not just heat it up more. In December 2022, the NF achieved something genuinely historic. We'll talk about that. But first, we need to go deeper, because Feynman saw a layer beneath all this engineering problem, and what he saw is what truly shatters reality. You know what the Coulomb barrier is. Two protons repel each other because they have a positive electric charge, and like charges repel. Simple as that, right? Feynman said no, it's not simple at all. In his lectures on physics and in quantum electrodynamics QED, which won him the Nobel Prize in 1965, Feynman reformulated what force means. Electrostatic repulsion between protons isn't a force acting at a distance, like Newton imagined. There's no classical mechanism where one proton pushes another from afar. What happens, according to QED, is exchange of virtual photons. Two protons exchange photons, not ordinary ones you detect with a camera or that warm your skin. Virtual photons, never detected directly. They exist in probabilistic superposition, temporarily violating energy conservation within Heisenberg's uncertainty limits. One proton emits a virtual photon, the other absorbs it. This exchange transfers momentum. The result, electromagnetic repulsion. Here's a way to visualize it. When two magnets repel in your hands and you feel that invisible force, what's happening microscopically is electrons and protons exchanging virtual photons, incalculable numbers per second. This exchange creates the pressure you feel. No force flows through space. There's a constant dance of mediating particles exchanged between charges. It's elegant, mathematically perfect, and completely different from any intuition about pushing and pulling. Feynman diagrams, elegant representations of particle interactions, aren't literal pictures. They're calculation tools. Each diagram represents a probability amplitude. Sum over all possible diagrams, any number of virtual photons, and you get extraordinarily accurate predictions of electromagnetic behavior. QED is the most precisely verified physical theory ever. Its electron magnetic moment prediction agrees with experiment to 10 decimal places. But Feynman asked the key question: why does virtual photon exchange produce repulsion? Why not attraction? Why does a proton emit a virtual photon at all? What does emission mean when the photon's undetectable? The QED answer? That's the rule. That's how the quantized electromagnetic field works. Proton repulsion is the observable manifestation of a mathematical framework that predicts reality with extraordinary precision, but fails to explain mechanically why reality has this structure. Feynman was brutally honest about it. In a famous interview, he said he could give a surface-level answer, but each answer leads to another deeper question. Eventually, you reach a point where the only honest answer is, we don't know. Quantum mechanics describes what nature does with uncanny precision, but not why nature chose those rules. Apply this to fusion. The Coulomb barrier. The core obstacle of the fusion problem isn't a classical wall with a defined height. It's a manifestation of a quantum field whose underlying mechanism has no mechanical explanation. When you calculate the Coulomb barrier with precision, you use QED, and QED is extremely accurate. But if someone asks why positive charges repel instead of attracting each other, the honest answer is that the mathematical structure of the universe is just built that way, and we have no idea why the universe chose this structure over any other. The main hurdle to fusion is something we calculate with absolute rigor, but don't understand in the slightest. If the repulsive force, the barrier that makes fusion so difficult, is a quantum field phenomenon with no mechanical explanation, what about the force that makes fusion possible? What exactly is the energy that reactors are trying to extract? This is where it gets even weirder. The binding energy curve is critical in nuclear physics. Horizontal axis, neutrons and protons in the nucleus. Vertical axis, binding energy per neutron in megaelectron volts. It rises sharply for light elements, peaks at iron 56, roughly 8.8 MeV per neutron, then drops for heavier ones. What this tells us, elements lighter than iron release energy fusing. Why? The fusion product has higher binding energy than the reactants. Elements heavier than iron release energy, splitting nuclear fission. Iron is the tipping point. For fusion energy, use hydrogen, deuterium, tritium. Deuterium-tritium fusion releases 17.6 MeV, enough that a cup of seawater could match 300 liters of gasoline if all its deuterium fused. But where does this energy come from? This is the point Feynman would insist you get absolutely right. A helium-4 nucleus-fused 2 protons and 2 neutrons weighs less than its 4 separate components. That's the mass defect. Through EMC2, this missing mass converts to energy 17.6 MeV for deuterium-tritium. That's the power from the reactor. But where was this energy before? It wasn't anywhere, not a figure of speech. Before fusion, deuterium and tritium exist separately, each with its mass. No hidden reservoir of binding energy waiting. Binding energy isn't stored inside the nucleus. It's an emergent property of the bound system. When they fuse, the system drops into lower energy configuration. The difference becomes kinetic energy of the resulting particles. Mass vanishes. Energy appears. Etron MC2 says they're the exact same thing. Feynman would appreciate the weirdness. Why does the binding curve have this shape? Why does the strong nuclear force, the residual effect of quark interactions mediated by gluons, peak at iron 56 instead of some other element? Why is the universe structured so hydrogen fusion releases energy instead of absorbing it? We can calculate the binding curve from quantum chromodynamics, QCD. The math works. Predictions hold up. But mechanistic explanation for why QCD has these parameters, why the strong coupling constant has this value, why the universe has this structure doesn't exist. Here's a distinction Feynman would make. What glues protons and neutrons together isn't technically the strong nuclear force. It's the residual strong nuclear force, the nuclear analog of van der Waals forces. The strong nuclear force itself acts between quarks, mediated by gluons, QCD. What acts between protons and neutrons is a residual effect, mediated by pions. Even nuclear physicists work one abstraction level above fundamental physics, abstractions all the way down. In December 2022, the ENIF did what had never been done. A fusion experiment produced more fusion energy than laser energy delivered to the target. 192 lasers focused 2.5 megajoules onto a pea-sized deuterium-tritium pellet. Result: 3.15 megajoules of fusion energy. True energy gain, first ignition. For scale, 3.15 megajoules is roughly a speeding car's kinetic energy, tiny in absolute terms. But for what the experiment proved, one of the most important moments in 21st century experimental physics, a milestone that took decades, history books stuff. But let's be precise about what happened and what didn't. The 2.5 megajoules delivered to the target required about 300 megajoules of grid electricity to generate. Lasers have terrible efficiency, about 0.7% conversion from electrical energy to laser light. So energy gain relative to the target? Real. Energy gain relative to the power grid? Still massively negative. NIF was designed as a scientific weapons physics experiment, not commercial energy. Ignition was the scientific goal proving the physics works. And it did. The commercial path is different. ITER, the largest tokamak ever built, is designed to produce 500 megawatts from 50 megawatts input. That's a tenfold gain. If it works as designed, it's the first fusion system to sustain plasma in burning conditions for extended periods. Won't generate grid electricity, it's an experiment, but it demonstrates physics and engineering at real scale. Commonwealth Fusion Systems is developing high-temperature superconductors for stronger magnetic fields, potentially shrinking reactors substantially. Helion Energy extracts electricity directly from plasma instead of steam turbines. TAE Technologies explores alternative fuel cycles. Progress is genuine, diverse, and accelerated by private capital that didn't exist 10 years ago. But even if Commonwealth delivers a commercial reactor next decade, even if ITER works, even if fusion becomes humanity's primary energy source, will we understand why fusion works? Feynman had a specific answer to this. In 1981, the BBC filmed Feynman for Horizon. The interviewer asked why magnets repel. Feynman said he could answer. But first, he wanted to explain what kind of answer he'd give. He spent several minutes describing the philosophical problem of answering why in physics. When you ask why magnets repel, you want an explanation in familiar terms. Magnetic repulsion comes from fields. But why do fields behave this way? Because Maxwell's equations describe electromagnetic reality. Why Maxwell? Because the universe has field structure. Why this structure? It just does. There's no deeper level where the answer becomes intuitive, because quantum reality isn't intuitive. It's mathematically precise and conceptually strange. Feynman concluded, scientific honesty requires acknowledging this limit. Physics predicts and calculates with impressive rigor. It doesn't and may never provide a mechanistic explanation that satisfies intuition about how things should work. But Feynman wasn't being pessimistic. Acknowledging this limit is what makes science honest and what sets it apart from pseudoscience, which pretends deep explanations while really just stacking words over phenomena we don't understand. I don't know is one of the most scientific statements that exists. It opens the door for the next generation. Apply this to fusion. Why does quantum tunneling let protons cross the barrier? Because quantum mechanics describes particles as probabilistic wave functions that propagate through barriers. Why does quantum mechanics work this way? Because the universe is quantum. Why is the universe quantum? Feynman said nobody understands quantum mechanics, not in the sense of an intuitive explanation. We apply it with extreme exactness. We predict experimental results with superhuman precision. We don't have a mental picture of what's happening that's true at deeper levels. Why does the Coulomb barrier have this exact height? Because proton charges and QED constants have these values. Why these values? We don't know. Why does binding energy peak at iron 56? Because QCD has these parameters. Why? We don't know. The great misconception isn't just that people think temperature instead of tunneling. It's deeper. People, including many experts, confuse calculating with understanding. NIF achieved ignition not because we understand fusion fundamentally. We achieved it because we got the math right and built hardware to run what the math described. Physics worked because physics always works, not because we finally understood why. Feynman would say, "This isn't frustrating. This is exactly how it should be." Nuclear fusion operates at the deepest frontier of known physics. An electrostatic barrier exchange of virtual photons, described by the most precise theory humanity's developed, with no mechanistic explanation for why the universe chose this mechanism. Quantum tunneling that lets particles appear on the other side of classically insurmountable barriers, perfectly calculable, conceptually indecipherable at the deepest level. Energy release via mass deficit obeying ERMC2, where energy and mass are the same thing described two ways, where the energy doesn't come from anywhere because anywhere doesn't apply to quantum systems. This isn't an engineering problem waiting for a solution. It's a quantum phenomenon humanity is learning to tame without fully understanding why the universe allows it. Feynman serves as guide because he was the most honest physicist about the distinction between calculation and understanding. He developed tools to calculate the Coulomb barrier, tunneling, binding energy with unmatched accuracy. And he said most clearly, these tools predict what nature does. They don't explain why nature is the way it is. Every watt from a commercial fusion reactor will be generated by a process whose deepest why remains open. Fusion will work magnificently, just as electricity works without you understanding QED to flip a light switch. But honest physicists will know they're operating a machine that perfectly performs something physics describes but doesn't explain. Feynman would celebrate this. To him, the unknown frontier wasn't science's failure, it was the most interesting place. Every answer that opens a deeper question means science is working. The alternative, believing we fully understand, is intellectually dangerous. It halts progress. This isn't just a story about energy technology. It's where human understanding ends and scientific honesty begins. Fusion is where humanity's most advanced physics faces unanswerable questions and moves forward anyway. NIF proved calculations work. ITER will prove engineering at scale. Private companies will likely prove commercial grid-connected fusion within this generation. None of these will answer why the universe lets fusion work. That stays open. If Feynman were alive, he'd celebrate every single watt and insist, mastering something you don't completely understand is science in progress. If this changed how you think about fusion, about calculating versus understanding, where physics ends and mystery begins, share it with someone who thinks they know fusion. And if you want to keep seeing physics from Feynman's angle, the next video's waiting.